Right, so far we have seen the addressing modes with the instruction formats and the number of words and the number of cycles that it can take. And we have seen how we can disassemble a machine code or hex code into a proper assembly language. And we have to see some assembler operators, as you can see on the table over here, where we can use add, minus, multiply, divide, and, or, XOR, shift left, shift right. So these are some of the assembler operators that we can use while we are writing an assembly. So you can do 5 plus 3. You can do 9 minus 3, 5 times 7, and 8 over 2. So it's going to be the result of those stored in the registers. You can also do the AND, depending on what you want to AND together. It has to be two values, forward or as well, and XOR. Shift left, you can use these arrows pointing to the left, and shift left by X, that means shifting left by 1. This is shifting right by 2. Okay, so you can do that by using those assembler operators. Another important thing is assembler functions like high and low. So, for example, LDI R20 low, let's say 0 hex 1, 2, 3, 4. What does that mean? This is actually means, or let's write the other line as well. LDI R21 high 0 hex 1, 2, 3, 4. So when we are saying low, it means, so we have got the value 1, 2, 3, 4. So the low means the low byte, which is 3 and 4. So this is what it's going to store in R20. And high means high byte. Maybe I should use a different color. And that will be 1 and 2. Okay, so this is how we can use a assembler function high and low in order to store the bytes into the registers. So rather than writing them separately, you can just write everything, and then you can just specify which one will be the low and which one will be the high. Another example related to these, LDI R20 low minus 200 and LDI R21 high minus 200. So minus 200 is actually, it is FF38 when you convert it to hex. So 38 is the low byte, and FF is the high byte. Okay, so this is how we can use low and high. Now, I want to solve a couple of examples related to what we have done so far, so that we can understand how we can use addressing modes or different types of instructions so that we can do some operations with those. So here is the first example. Write a program starting at flash address 0 to copy the value x55 into memory locations 140 to 144. Use Y pointer for indirect addressing. Now we have done a similar example to this, but I just want to revise it. So we have to start from address 0. That means we have to write .org 0. This is an assembler directive telling to the assembler that we will start writing at address 0. Then I have to do this 5 times, 140, 141, 142, 43, and 44. So I need to define some counter, LDI R19 or R16, 0 hex 5. So I'll also write comments over here. R19 will be 5 for counter. Then the next thing that I need to do is I have to load this value into GPR before I load it into the memory locations. So R17 is going to be 0 hex 55. So R17 is equals hex 55, and that should be the value copied. Now I have defined those. Then I have to define the Y pointer. So the location is 140 and 144. So we had to define the starting location of the Y. So LDI YL 0 hex 40. So that will be the low byte of Y with the value of 0 hex 40. Then LDI high byte is going to be 0 hex 01. And we can say load the high byte of Y with the value of 0 hex 01. So we have defined the Y register locations, and then we can say store R17, which we need to copy into Y. So copy R17 to memory location 0 hex 140. Then of course it will be incremented. So we increment the low byte. So increment low byte of Y. And then we have to decrement the counter, decrement R16. And then branch not equal L1. So we have to loop until counter equals 0. So loop L1 should be here. So let's reorganize this so that everything is in an order. Right, so as we have already done this, we are just loading the address of Y. We are storing R17, copying hex 55 into Y, 140, and then we increment it to 141. We decrement the counter, and then we loop it until we reach to 144. So we have said that this is one way of implementing this. If we want, we can modify it. So if we go further, this is what we are getting as well. Then we can use low and high assembler function as an alternate. So rather than writing this as LDI YL hex 40, I can just write this as LDI YL low 0 hex 140. So I can write the complete address, and assembler will decide what will be the low byte and what will be the high byte. And I can repeat the same thing for LDI YH high 0 hex 140, or you can just write 140, and that will load the high byte of it. So we can use this high and low during when we are defining the low byte and high byte of Y. So you don't need to care about which one will be high, which one will be low. Our assembler will take care of that. And that's done. And then we can use also post increment version like we have done it before. So we can modify this Y as a Y plus, and we can actually get rid of the increment line over here. And that's it. We get rid of one of the lines. So this is the most optimized code that we can write for this program. Well, so the next example, assemble the previous assembly code in both binary and hex and show the program memory address for each instructions. Okay, so now we are doing the reverse engineering of disassembling. We have to assemble it. And in order to assemble it, let's move down a little bit. We have to know the instruction formats, which they are given us in the data sheet. So I'm going to provide it over here so that we can go through together in order to assemble it. Okay, I'll write the titles over here. Let's say this is the address. Then content in binary, content in hex. So let's deassemble it and find out what will be each of those instructions are going to be. Okay, so the first instruction is LDI instruction, which we have to start from address 0. So I'll just write 000. Then contents in binary. What do we know about LDI? The opcode is 1110. Let's give a space so that we can see what's going on. Then we have to have the value constant, which is 5. So this is actually 05. So 05 is going to be written as 000. And then we need to have the destination, which is 19. So if 16 is 000, 19 is going to be 16 plus 3. So this is going to be 0011. And then we can write 0101. So this is the content in binary for the first instruction, LDI R19X5. Now the content in hex, in this case, it's going to be 1110 is E, then 0, then 3, then 5. So this is the content in hex. Then we carry on with the next address 0001. Now 001, it's going to be another LDI 1110, and that will be in 55. So 55 is 01015, and then R16 is 000, and then another 5, 0101. So the instruction is E505. That will be our next instruction. Then I carry on 002, then it is 1110. Now register Y. Register Y is 28 and 29. So we are starting with YL, which means 28. Now the value that we want to copy is 40. So I write 4 first, and then 28 is 16 plus 12. So 16 plus 12 means 16 is 000, 12 means 1110. 1100. Sorry. And then I have got 0 as the last value of it. And this is the content in binary, which is equivalent to E4C0. Then I repeat. So the instruction 3 is going to be address 3. We have got LDI and high byte. So that will be 01. So 0 over there, and it has to be 29, which we need to add 16 plus 13. That is 29. And then we have got 001. And this will give us E0D1. Then we carry on. So we have done the LDIs. The next instruction is store. Store is 100, 004. So 100, store Y. And then 001 is still the instruction. Then we have got RRR, which is R16, which is going to be 1000, and then 1000. So the hex content, it's going to be 8308. And that's instruction 4. Then instruction 5, we have got increment YL. So what is increment? 1001. 010, and the destination is YL, which is R28. Now R28 is going to be 11100, and then the last opcode of the increment is 0011. Now this is going to be 95C3. Then decrement R19 is instruction 6. Decrement is 1001, 010. R19 is 10011. And then we have got the last part of the instruction opcode is 1010. And this is 953A. And the last instruction is the branch instruction, which is 007. So the branch instruction starts with 111 and then 01. So the branch value that we need to have is, now we have to think about it carefully. Where do we need to jump? We have to jump back to 1, 2, 3 steps. So in order to jump 3 steps back, that means we have to consider program counter plus the K, which is going to be program counter has to be 2 in this case. So it has to be -2, sorry, 4. So, so the value that we are going to get has to be -4, and then +1, it's going to be -3, that we need to jump 3 steps back. So we can get that as 1, 1. You can take the complement of it, 1, 1, 1, 0, and then 0, 0, 0, 1. And this will give us F7 E1. So that's how we can assemble the code, and we can write it with the addresses and the contents by using the instruction formats and assembling the Ks and the Ds and Rs based on the instructions given. We can easily write the content in hex. Okay, so we have the solution over there as well. Then two 32-bit numbers are stored in memory locations 130, 133, and 150, 153 between in little endian notation, so low address gets low byte. Write a program to add the two numbers and save the results in address 160, 163 between 116 and 163. Use indirect addressing XYZ pointers. Okay, so programming example 2. Now what do we have? We have got two 32-bit numbers, and we have to specify some addresses, which we need to use the pointers in direct addressing. And we can actually use all of those because we need three locations. So X, Y, and Z can be used for each of those. And then we have to, when we load them, we have to get the contents, add them together, and then store them to this location. So let's try that. We'll start with LDI. Now we have to store it into, that's 1 byte, 2 byte, 3 byte, 4 bytes. 4 locations, and we have to store 4 bytes. So let's set a counter LDI R16 0 hex 4. So R16 is equals to 4 as a counter value. Then let's define address for X first. LDI XL, it's going to be low byte of 0 hex 130. And then LDI XH high byte of 0 hex 130. So I can write a comment as load pointer X equals 130. Then I have to do the same thing for the second part, address, which is 150 to 153. So LDI YL low 150, 0 hex 150, LDI YH high 0 hex 150. And we can say load pointer Y, which is equals 150. Then LDI ZL, so the low byte of Z is 160. So based on hex 160. And then LDI ZH high 0 hex 160. So we have initialized all the X, Y, and Z pointers based on the given addresses. Now, what we need to do is we have to think about how are we going to do the addition. Now, as these are 1 byte, that 1 byte has to be added with that 1 byte, 74 has to be added with 98, 65 has to be added with 78, and C7 will be added with 29. So I have to get these values from the memory locations. Okay, so we have to get these from the memory locations, store it in the GPRs, and then we perform the arithmetic operation. But before perform the arithmetic operation, I'll use CLC to clear carry because we need to use clear carry as we have to do 32-bit operation. Now, I have to use load instruction, which it will load the memory content into GPR. So let's say R18, will be used. And I have to load the content, the content of the first byte. So X, I'll use X plus post increment method. So I can say copy memory to R18 and increment X. Then I do same thing for Y because I have to get the location 150 content. So R19 Y plus, copy memory to R19 and increment Y. And then what do we need to do? We have to add these two together. So I'll use add with carry. And that will be R18, R19. So R18 is going to be R18 plus R19 plus carry. So we perform the operation. And then once we got the result in R18, I have to store it into 160. So store Z plus R18. Again, with the post increment, we'll start with 160. So store R18 in memory and increment Z. Then once we have done that, we can decrement the counter because we've done the first byte and we move to the next one. So decrement R16. Then we can say decrement counter branch not equal L1. So we can say loop until counter equals 0. And we have to loop it from here because that has to be repeated. Okay, so this is how we can. We have to define the addresses into the pointers, and then clearing carry is a good thing because you are doing ADC. So then we load the content into R18 and R19. We perform the addition. We store it back into register Z, which is 160. Decrement the counter and repeat it until it is done. So this was program example 2. And example 3, add two 16-bit numbers stored in memory locations 130, 131, and 150, 151, and save the result to the first location. Use indirect memory addressing with displacement. So after initializing the pointers, your program should do the addition in a subroutine. So we have to also create a subroutine so that we can do the addition. Okay, let's see how are we going to do that. So we have to add two 16-bit numbers stored in memory locations 130 and 131 and 150 and 151. So if I'm going to use a subroutine, okay, in order to define a subroutine, we have to initialize a stack pointer because we are going to call a function and that function call has to store the program counter value into stack. So I have to initialize the stack. So let's start with LDI R16, the high byte of Rament. Rament is defined in the definition file. So normally, when we are writing the code, actually, we have to include the definition file. So I suggest you to write it. Include m128 def file.inc, and that is our include file. So high byte of the RAM out where it's going to be the stack pointer high byte R16, and LDI R16 low Rament, and out SPL R16. So I'll say initialize the stack pointer. So that's showing the initialization of the stack pointer. And next thing to do, we have to initialize the registers that we are going to use. So as we are going to use displacement, we have to use register Y and Z. So in order to do that, LDI YL low 0 hex 130, LDI YH high 0 hex 130. Then LDI ZL low 0 hex 150 pointer address, and LDI ZH high 0 hex 150. So we loaded the pointers. Let's say load pointer Y 0 hex 130 and load pointer Z with 0 hex 150. Now, as it's saying that we have to initialize, after initializing pointers, your program should do the addition in a subroutine. We initialize the pointers. Let's call the subroutine. Let's say add call add long or add 16, whatever you want to call it. You can have any function name over there. I just use add long. Now, add long function, we have to define it here. Let's clear the carry at the beginning. Then we have to load the value in Y into one of the GPRs. So LD R18Y. So we have to be careful over here. We are copying low byte of first number to R18. Then load R19Z, copy low byte of second number to R19. Then we have to do ADC R18, R19, and R18 is equals R18 plus R19 plus carry. And then we have to store the sum, store Y R18. So store sum of the low bytes. Okay, now as we have done this, the next thing to do is, because we are using indirect memory addressing with displacement, what we need to do is we have to increment it with the constant q. So y is going to be incremented to 1331 and z has to be incremented to 151. Now, in order to do that, I can use an instruction LDD, indirect with displacement, and I can say R18, it's going to be y plus 1. So this is actually saying that copy high byte of first number to R18. So what we have done is, rather than repeating like we have done it in the previous one, like over here, looping it, I can just use displacement because I just need to change the value one time. And I have to do the same thing for R19, which is Z plus 1, pointing to the next Z address or the value. So I can say copy high byte of second number to R19. So we have got LDDs with indirect displacement, and we do ADC again, R18, R19, and then we have to do store, and that has to be displacement as well. Where do we need to store it? We have to store it into y. So that means std y plus 1 again, displacement, R18, store sum of the high bytes. And then, as this is a subroutine, I have to return back from subroutine to return back to here. So I have to use return so that my stack will be reinitialized to the point where it is left. So that's all I need to do, and that will be our solution for this problem with indirect memory addressing with displacement, initializing the pointers, initializing the stack, and doing the addition.